So today his title of the presentation is New Ultra High Speed Device Concept from terahertz nanoplasma devices to glass-like electronics for neuromorphic computation. So uh, Mohammad, so time is yours. So please start anytime.
Thank you very much for the invitation, and it's a pleasure to present here. So I hope you can see my slides now.
Yes, okay.
Okay, great. So hello everyone. My name is Mohammad Samizadeh, and I want to talk about new device concepts for ultra high speed electronics. So we can see in general electronics in three major categories. So we have RF electronics that we use every day for communications and other applications such as navigation, imaging, and sensing. We have logic electronics for data storage and information processing, and also power electronics, which we use for energy conversion, and also motor drives and other high power applications that we have. And if we take a look at the frequency operation and power or voltage operation of these devices, they operate in very different range of frequencies and powers. And we can see from like tens millivolts to 10 or 100 kilovolts even, and in frequency from like kilohertz range all the way to the terahertz range. And we can see that these electronic devices are kind of limited in power and frequency, that here we show them by dashed lines. And we can see that these limitations basically limit the performance of our electronic systems today. For instance, we can consider RF electronics, and we can consider the power frequency trade-off, which is this dashed line, PFS square limit. And this limit basically limits the operation frequency and the power of RF systems, which at the end limits the communication systems that we have, kind of data rates that we can transfer and so on. And the same thing for logic electronics. We want them to operate at very low voltages and very high speeds, but there are very strict limits for semiconductors, such as thermionic limits, which limits the subthreshold, the slope of the devices, and limit the bias voltage that they need. And these limitations basically also limit the performance of logic systems. So in this talk, I want to present some new device concepts that can in fact overcome some of these limitations in this graph, and basically they can unlock some operation regimes that are not possible today with our conventional electronic devices. And in particular, I will focus on RF electronics at a terahertz range of frequencies, as well as logic electronics. So the outline of my talk, I will discuss about three main device technologies. First, I will discuss about nanoplasma devices that can, in fact, tackle this particular limit, PFS square limit, and they can, in fact, generate power for us at very, very high frequencies, breaking the power frequency trade-off in semiconductor devices. And then I'll talk about electronic metadevices, which can push the cutoff frequency limit, this limit at the higher end of this graph. And basically with this device technology, we can have devices with extremely high cutoff frequencies. And at the end, I will talk about devices based on vanadium dioxide, which can enable a new way of computation for us at very, very low voltages that can in fact target this limit, important limit in logic electronics. They are also relevant to neuromorphic computations. Okay, so I will start the talk with nanoplasma devices for terahertz generation. So we are all familiar with the terahertz gap. This is the range of frequencies between microwaves and optical frequencies. So at frequencies below about 100 gigahertz, we have robust hardware. We have electronics that can operate in this frequency regime, electronics based on MMICs. It's an integrated electronic system, very functional and very robust performance at frequencies kind of below 100 gigahertz. And if you look at frequencies above 10 terahertz on the other side of the gap, we again have robust hardware based on photonic devices. And between the two, basically, we don't have a good devices, good hardware to be able to operate. So, and here we can see this limit. So if you look at the output power of electronic systems, they drop sharply with frequency. And in fact, at 1 terahertz, we can say that we have basically no power or very, very small powers. Also, in the other side, from optical devices, there is a drop again when we approach 1 terahertz. So in the other side, quantum cascade lasers are the mainstream devices that can operate. But still at 1 terahertz, they need cryo temperatures and also can deliver very low power. So at the end, that's the limitation that we have at terahertz frequencies. And in particular, if you take a look at the electronic side to see where this limitation is coming from to be able to maybe resolve that, is that if you take a look at a very simple amplifier with a single transistor that can in fact operate at the highest frequency that we can have today, these simplest amplifiers, class A amplifiers, we can see that in fact, if we consider semiconductor devices, their saturation current, the range of saturation current that they can have is something around 1 milliamp per micrometer. So any kind of semiconductor, high performance semiconductor device that we take, we obtain a current, the saturation current in this range, 1 milliamp per micrometer or 1 amp per millimeter. And then we have a output capacitance. This is a parasitic capacitance, like a coplanar capacitance that we cannot really do anything with that. It's there. It's a parasitic capacitance, and that is about in range of 1 femtofaraday per micrometer. And it's very interesting because when we want to switch this device, the very first thing that this current, this channel current has to charge and discharge is its own output capacitance. So we have a C out that needs to be charged and discharged. And this, in fact, dictates a kind of a slew rate to the system that we can see in this graph. So basically, if we divide this current and by this capacitance, we see the dVdt, or the slew rate of the transistor, which is about like 0.5 volts per picosecond, which means that if we have this, if we take a look at this graph, the red curve, the red sine wave, basically we have this dVdt, we have this slew rate. This is at power, is as frequency f and power 4p. And then if you want to double the frequency and go to the blue curve, because we are limited by this slew rate, in fact, we lose 2 times in amplitude and 4 times in power. And this dictates the kind of PF square that we can achieve by this semiconductor device. And we can see this limitation in a state-of-the-art devices. This is the output capacitance versus the drain current. And we can see that this limitation of 1 volt per picosecond or below 1 volt per picosecond is there. This is one limit, and the other limit is dictated by the critical electric field, and the saturation velocity is known as Johnson's figure of merit. And it's very interesting that the devices with the highest mobility and highest cutoff frequency, which is gallium arsenide and indium phosphide, shows dVdt, the Johnson's figure of merit, even below 1 volt per picosecond. So this is the place that we see a limitation in the large signal performance of the devices, which at the end results in a PFS square below 10 milliwatt per terahertz, 10 milliwatt terahertz a square, which gives us almost, I mean, very low power at terahertz frequencies. However, if we can, to see how we can break this limit, we can think of other ways of doing electronics, other way of switching. And it's very interesting that the very first switches that were demonstrated has the potential to break this limit. And they were actually demonstrated much before the demonstration of the semiconductor devices and transistors. We can take a look at what happened in the early stages of electronics by Marconi. So this is basically the very first radio that was demonstrated. It was basically based on an LC component, a coil, and a capacitor, which we see here. And then the switch technology there was actually a spark gap. Let's take a look at this switching technology to see whether it can break the fundamental limit of semiconductor devices or not. So we can see here the voltage waveform of an spark gap switch, and it's very interesting to see that the kind of slew rates that can be achieved by these devices that are very giant, of course, we know that, it's much above what we can have with a semiconductor device. So this is a voltage over time, and we can see slew rates in range of 100 volt per picosecond. So it's very interesting that this switch technology has the potential to to give very high current, which outbalance the off capacitance, the parasitic capacitance, and give us very high slew rates that can now achieve high power at high frequencies. So what we did was to make these spark gap devices that Marconi made many years ago, more than 100 years ago, on the chip, and to be able to integrate them with other components, terahertz component that we fabricate on the chip to generate high power to see how it works. So this is the devices that we fabricated. These are like fabrication of a nano gap that we have on the chip. So here we have a coplanar waveguide, and we have a nano gap in between. Here is the SEM image of the nano gap. And to prove that we can in fact trigger plasma there, here we just made a device which is a bit larger to have an optical image to see that these sparks can shape up at the gap. So this is a 6 micrometer device, gap device, just to take an optical picture from that. And we can see that we can have a kind of planar structure of those spark gaps as Marconi made on the chip. And it's very interesting that the switching speed of these devices that we fabricated on the chip are extremely high. So here is the measured switching characteristics of these devices. We have voltage over time. And we can see that slew rates above 10 volt per picosecond can be achieved. And this is by itself 10 times higher than what is achievable by a semiconductor device. And we have to note that this measurement was done by a 70 gigahertz oscilloscope. And so the switching time is basically limited by the bandwidth of our experimental setup. So the switch is actually faster than what we see here. And to see these nice sparks, we took a video from them for the devices with a larger gap to be able to see the sparks. So I don't know if you can notice here. So we have a zigzag gap, and then we have made these sparks on the chip with a very high repetition. So maybe I can. So right here we have these tiny sparks on the chip. And these sparks give us a very good switching capability. And the way that they work is that, of course, initially they are in isolation mode. There is no current passing. It's a nano gap on air, nothing. So we increase the voltage and we have no current. And when we reach the threshold voltage of the nanoplasma in the gap, we form the nanoplasma, and this nanoplasma is extremely conductive. And it gives us a switching that is very fast from this point to this point. And this switching is extremely fast in the picosecond range. And we will show how we can use this technology to generate terahertz at high powers. So what we did here was to integrate these nanoplasma devices with bow tie antennas. So here we have two antennas in this figure. This is the first antenna, and here right at the gap, at the gap, we have a nano gap that we see the SEM image here, and then we have the arms of the bow tie antenna, and then we excite this bow tie antenna from this port. So we inject a very normal, this can be a microsecond pulse, it doesn't matter. So it charges the antenna until we reach the threshold voltage of the switch in between, right here. And when we reach to this point, we basically have the nanoplasma formation, which gives us a picosecond switching. And then we excite the bow tie antenna at its port with a picosecond signal. And what happens is that the antenna radiates a wave packet corresponds to its fundamental frequency. And then we have another bow tie antenna on the other side that picks up this signal, and then we analyze the output to understand the performance of this terahertz radiator. So here the bow tie antenna is the resonator and the radiating element, and here we see the different designs of this antenna from 50 gigahertz to 109 gigahertz. We basically just changed the geometry of the antenna to change the resonance frequency. And at 109 gigahertz, we directly measured very high powers, up to 50 watts, which, as you can see here, clearly outperforms the state of the art in radio frequency electronic systems. Um, yeah, and so perfect. So, and after 109 gigahertz, we designed an experimental setup to characterize the performance of these devices at a real terahertz band at 300 gigahertz to see how they can work at those range of frequencies. So as you know, in this range of frequencies, we cannot use oscilloscopes because I mean, the highest frequency of oscilloscope barely reaches like 100 gigahertz. And here, what we can do is to use down converters to be able to measure these devices. So this is the schematic of the experimental setup that we had. So this is our terahertz probe station, and here we have the device under test. From the left side, we excite the device by a normal wave. This can be a microsecond wave, it doesn't matter. And from the other side, when we pick up the terahertz signal that we generated, we have a mixer. This is a commercial mixer that down converts the signal to intermediate frequencies. And at the end, we could measure that by a 70 gigahertz real-time oscilloscope. And these are the signals that we achieved. So in the left side, we see the experiment. So this is the signal that we measured at the oscilloscope. This is after down conversion. And we can see the intensity of this signal, and in order to identify the power that we received, the terahertz power that we received, we in fact used a reference terahertz source. This is the dashed line here shows a 2 milliwatt CW terahertz source, and in fact, based on the ratio between the two, we identified that we received 25 milliwatts. So this is not the radiated power, but the power that we received at the other side, which is by itself a very high number. And the waveform that we received also matches quite well with the simulations that we performed. And a very interesting point is that now with this experiment, we could comment on the real switching time of the devices. How we did that? So in the simulations, we changed the switching time of the nanoplasma devices, and we simulated the amount of received power in our system. So here is what we see. So this is the received power versus switching time. And you can see that it basically starts from about 25 milliwatts at very small switching times. And if the switch has a switching time above 2 picosecond, which is this point, our simulations show that basically we shouldn't receive a high power at the receiver. And now if we compare these numbers with the number that we achieved by the experiment, it shows that we are almost in this corner. So we can say that by high confidence based on these results, that the switching time of the nanoplasma devices is below 2 picosecond, which is a very short number. And now this is below 2 picosecond. We cannot identify more. We cannot understand better the switching time, but we know that it's below 2 picosecond. It could be 1 picosecond, it could be 100 femtosecond, but this shows promising results for these devices. So, and then we this was the received terahertz power, and then we obtained and then we calculated the power that we transmitted by the S parameter between the transmitter and the receiver antenna. So this is the S parameter that we measured, this red line, which agrees well with the simulation that we have between the two antenna. And based on this S parameter, it turns out that the radiated power from our source was about 2 watts at 300 gigahertz, which again indicates that this device technology can outperform state of the art in conventional electronics. So here we end the section about the nanoplasma devices, and we talk about electronic meta devices in the second part of my talk. So contact resistance of semiconductor devices is a major limit on their performance. So in fact, we have a very high quality, very nice channel in the device, and then we can control that by a very short gate. But in fact, in order to have access to the devices, we first need to inject electrons to this channel through tunneling junctions and extract the electrons from the other sides, again from the tunneling junctions. And if we take a look at the state of the art contact resistances that people can achieve in semiconductor devices, it's, I would say, way above 30 ohm micrometer, which by itself is equivalent to a 100 nanometer long channel semiconductor device. So we have a very nice channel, but the entire thing gets dominated by the contacts. And this is a major limitation on performance of semiconductor devices, which limits their performance at high frequencies and also produce losses for these devices. And here we see also the strict limitations on the contact resistance of different technologies, and this exists in different material systems from graphene to gallium nitride. So here we are talking about a very major and very general shortcoming for the devices. And we can see this clearly in very high performance devices. So this is an example of a very high performance gallium nitride transistors, which are very interesting for today's communications, for high power, high frequency operation that we need in 5G and 6G communications. And here we can see that the channel resistance is lower than the contact resistances. And so the performance of this device is totally dominated by the parasitics of this electron injection. And then we were thinking how we can potentially resolve this limit. And if we can mitigate this limit, in fact, we can boost a lot the performance of high frequency devices. And this is a major thing. And we thought that, okay, one potential way of doing that is to use displacement field coupling or electromagnetic interactions uh, between the metal and the semiconductor underneath. So here we do not inject electrons from the top metal to the semiconductor, But what we need is that we rely on the displacement fields to couple power from metal to semiconductor. So here we have a coplanar waveguide. Here we have the device. We have the 2D electron gas here, and we have two simple terminals. And here we see the cross section of the device. So in simple words, we can say that we form some kind of capacitance between the top metal and the 2D electron gas, noting that they are very, very close to each other. They can be close like with like 5 nanometer distance or 10 nanometer distance or so. And through this coupling, we can inject a radio frequency signal from metal to the semiconductor. And then on the other side here, we can have it in the terminal 2. And if we apply a bias to terminal 2, let's say, we can deplete the 2D electron gas underneath, and we eliminate the displacement field coupling, and we turn off the device. So this is a way to realize a functional device, in this case a switch, without relying on electron injection. And we'll see how these devices can work. And see here we see a TEM picture of the devices that we fabricated with channel length of 50 nanometer. So we characterize these devices. We first started from devices with the straight gap, like what we showed in the previous slide. And here we can see that, in fact, we changed the widths of the device, and we measured the conductance and the capacitance of the devices. And as you can see, and as we expect, there is a linear increase in the conductance by increasing the widths of the devices. And with the same rate, we increase the capacitance. So if you look at the cutoff frequency of the devices, we are about 2 terahertz, which is comparable to Schottky barrier diodes. Interestingly, when we change the straight gap here by a stripe array in this form, like a multi-finger structure, we had a very interesting observation. And the observation was that the conductance of the devices grew superlinearly with scaling the device, while the capacitance was just linear. And then we outbalance the relation between the capacitance and the conductance, and we obtained cutoff frequencies much higher than what we got with the straight gap devices. And we can see that these devices can now go towards like outperforming state-of-the-art electronics. And this was a very interesting observation. And in the next slides, I will go through the mechanism of that and how we can achieve a very high performance device based on this concept. So the very first thing is that, so I said that let's say this is a capacitive coupling between the top metal and the 2D electron gas underneath. But the truth is that if you look at the Maxwell's equation at the barrier, this is not a normal capacitive coupling. So here we basically have the Z component of electric field, and we have a J component for the X component for the current density in the semiconductor layer. So here we have the X and Z direction. And then based on this mode, I would call it a mode, uh, initiates an electric field in the X direction. And we call this a TM mode, and the equation corresponds to this mode is written here with the K, with the K of the mode, which is extremely high. It is imaginary and it is extremely high. And if you look at the profile of electric field, the EZ, which is the displacement field, it determines everything in the barrier. Uh, Close to the gap, we see that we have oscillations that happen in micrometer range. So we have radio frequency signals. Their wavelength is very large. It's in millimeter range. But if you look at the wavelengths of this artificial mode, it's within micrometers. And this is because this K is huge. And as you can see, it damps. Why it damps? Because this is imaginary. So this is a kind of mode that is different from a normal capacitive coupling that happens in these devices. So this is number one the fact number one in these devices. And we can compare the profile of electric field with the conventional capacitor. If we replace these 2D electron gas by another PEC, we see a uniform EZ electric field, which is very different from the oscillatory damping behavior in these devices, which originates from these 2D electron gas. And then we can see that, all right, let's go from one terminal to the other. And let's take a look at the voltage drop across the terminals. For an ideal device, we want this voltage drop to be very small, right? To have a very high transmission. So if we calculate the line integral of electric field from point A to point E, point B, so integral EDL, E dot dl, we have two terms across the barrier, and we have the gap. The gap is something that we cannot do anything with that. It's the intrinsic part of the device. But the extra components that come from the gap, from the barrier, sorry, which is 2 times EZD, this gives us an extra component which results in a potential drop, which results in losses in devices, and which limits the conductance of the device and limits the cutoff frequency of the device. And we can see clearly this point in the simulations that we did, the three-dimensional simulations. So here we are looking at the EZ at the barrier, and we can see these oscillations, which we do not expect in a normal capacitor. And second, we can see that, in fact, there is a huge polarity shift right at the gap. So here we have blue, dark blue, and after the gap, we have dark red, which means that we have two components like this, and these two components means that we have a huge drop on the device. And we can see here clearly this sub-wavelength mode, the wavelengths of this sub-wavelength mode compared to the ordinary TEM mode of the device, and we can see how smaller it is. So this scale bar here is basically 1 micrometer, and we have very short oscillations on the devices. So this is the case for the straight gap device. And we can see that the contact resistance of these devices over frequency drops with 1 over a square root of f, which is the wavelength of this sub-wavelength mode. So the higher the frequency, the shorter the wave, the more confinement we have, and the lower losses we have in the devices. However, very interesting point is that when we go to the other geometry, to the stripe array, the shape of electric field at the barrier totally changes. So this is the geometry of the device, and here the electric field at the barrier. So let's take a look at two stripes close to each other. As you can see here, the shape of electric field is totally different. And the very interesting point is that these are connected to two different terminals, right? But if you look at the color, they are both red. It means that instead of a different polarity that we had on the straight gap devices, we now have electric fields along the same direction. And we will see that this is a key in the high performance of these devices. And if we take a look at the contact resistance, the measured contact resistance, we see a huge drop, which goes even below the 30 ohm micrometer, which is like the very best state of the art in electronic systems. So the way that this device gives a very high performance is in fact due to this manipulation of electric fields. So again, we take a look at the barrier at the cross section from terminal 1 to terminal 2. And again, we want to integrate E.dl from A to B. And in this point, we have a different kind of situation because now the electric fields in the two sides are in the same direction. And if you take a look at the integration, they basically cancel out each other, which is very different from the case of straight gap devices. And now the only term that remains in the line integral of electric field is basically the gap. So this device can give us an almost ideal contact or ideal coupling between the metal and the 2D electron gas underneath. And this is the key in the very high conductance of these devices. And here we can compare the distribution of electric field in the conventional electronic device with the straight gap and with the stripe array devices. And we can see that the pattern are very different. And because we could obtain such high performance with the manipulation of radio frequency fields in the subwavelength, we call this concept electronic meta devices because in terms of concept, it shares some similarities with optical metamaterials, metastructures, because in that sense, they manipulate optical fields and obtain exotic optical properties. Here we manipulate electronic radio frequency fields and we obtained exotic and very high electronic properties. And so this is a new concept that we called electronic meta devices. And we can clearly see these oscillations in the case of electronic meta device, while in the case of a conventional device, you have a huge discontinuity in the electric field. And here we can see the confinement of the current in the 2D electron gas. So this is the consequence of the field manipulation. In the conventional devices, we have current in the 2D electron gas all over the place. And this is not good because we have a loss, we have a high loss, we have a low conductance, and we have a low cutoff frequency. In the case of electronic meta device, however, we confine the current right at the gap. And that's why we have a very small loss and very high conductance. And as a consequence, a very high cutoff frequency. So this is a unique thing about this new concept. And the very interesting thing is that in this device, we have a kind of superlinear scaling for the meta devices, which means that when we increase the number of fingers, we have more and more confinement of current in the 2D electron gas. And here we can compare the case of two stripe devices with 8 stripe devices. And we can see that the confinement here is 2 micrometer. In this case is 1 micrometer. And for this reason, we have much higher conductance and higher cutoff frequency. So we realized such devices on an indium aluminum nitride and gallium nitride high electron mobility platform. We fabricated devices with different geometries for different frequency bands from microwave to terahertz. And here we see the parameters that we realized. And we performed state-of-the-art measurements up to 1.1 terahertz to evaluate the performance of these devices. So these are very, very difficult measurements. So here we see the experimental setup of our setup up to 1.1 terahertz. And so these are the terahertz probes with waveguide connections that go to the frequency extenders to have the VNA measurements. And here we have the device under test. And here we see the SEM image of the devices, and we can see the off-state impedance and the on-state impedance, and we can see a gigantic switching at 1 terahertz. This is a direct measurement, so this is by itself much better than like many state-of-the-art electronic switches. And we extracted the figure of merit, cutoff frequency figure of merit of these devices to be 18 terahertz. And here we have the C off versus R on benchmark of these devices that we realized versus the state-of-the-art electronics. And we can see that they can outperform the best performances in electronics. And we note that the way the people define the figure of merit of a switch is based on R on and C off, because this is a model of the switch, and at some frequency, the on-state impedance and the off-state impedance, which is 1 over omega C off, equals. And this is the frequency that the switch doesn't operate anymore. And this is the way they extract the cutoff frequency or the figure of merit of the device. So we evaluated the contact resistance and the total resistance of these devices. So here we have 3 sets of devices that we fabricated, and we can see that their contact resistance and their total resistance is much below what can be achieved by devices based on tunneling junctions. And it's very important to note that with considering very high conductance, these devices also shows very high breakdown voltage. And this is because we do not rely on ultra scaling anymore. Even a 120 nanometer long channel give us a very high conductance and a very high cutoff frequency. And if you look at the breakdown voltage of these devices, so here we see that we obtained about 30 volts of breakdown at a cutoff frequency of 18 terahertz, which is absolutely high. So if you work with terahertz devices, you see that they like break at very low voltages, and they can even break easily with electrostatic discharges. And then we realized a modulator, a 6G level modulator using this device technology. So here we have a two-terminal device, and in one side we inject a data signal, on the other side we inject a CW terahertz signal, and then the reflection from the device is basically the modulated wave. And we show that these devices can operate very well above 500 gigahertz, and a very clean modulation spectrum that we see here, and a very clean eye diagram that we obtained. And if you take a look at the modulation efficiency of these devices, they have a flat response up to almost 100 gigabit per second. And this is a golden number for 6G that can enable ultra high speed communications. We also fabricated three terminal devices based on this device concept. This is a three terminal meta device, and we can see the same kind of field pattern in the meta devices. It's not perturbated by the gates. We have the same mode, and we can have a very high performance switching of terahertz signal with the gate electrodes in this case that we see in this figure. And here we have the SCM image and the cross section of the devices. And the very cool thing about three terminal devices is that now we can realize advanced circuits based on this topology. And here is the experimental setup for the three-port modulator. In this case, we inject the CW terahertz wave here in this from this terahertz probe. We inject the data signal with this GSG radio frequency probe, and the output is the modulated wave, which is picked up by another terahertz probe. And then to analyze what we have at the output, we use the commercial mixer together with the high performance, high frequency oscilloscope to analyze the modulated wave. And here is the results of a three-port modulator, as you can see here. So basically this is the spectrum. We just shifted them to have a clear picture. So the shoulder here represents the data that we have. So we went up to 15 gigabit per second. This was the limitation of our data streamer. And here also we see very clean time domain signals, and also Q component versus I component to show the very good SNR for this modulator. And so here we close the second part, and very briefly the third part, which tackles some limitations in logic electronics. We have glass-like electronics for information processing. So it's very important to have very high-speed memory devices for electronic systems. This is because if you take a look at the conventional scheme for computation, if you want to do a computation, you need to read something from memory towards the ALU unit, performing the computation. And again, we have to come back to the memory unit to write the output. And we have to do it again and again and again. And we can see how much the speed of the memory devices will affect the speed of our computation. It's very significant. And also in more modern computation schemes, we can see that in in-memory computation, the role of memory devices is even more important because we do the computation also in the memory unit. So it's very important to have a high performance, fast and low power memory device. And we can see the benchmark here, operation speed versus cell size of different memory technologies. And we can see the ideal corner. This is the place that we want to operate in. So in the two other sides of this thing, so we have the hard disk, which is of course, very small, but very slow at the same time. And we have SRAM, which is currently like the fastest memory devices that we have, but the cell size is huge. So we cannot have a high density of memory, and also these are very like high power devices. Memory stiff devices are one pathway to have high performance memory and computational devices. But right now, because of device to device and cycle to cycle inconsistency, the large scale implementation of those devices are limited currently. So our approach was to use a MOT device, uh, a MOT insulator to perform electronics. So MOT insulator is a class of electronic materials that are based on conventional band theory are expected to be conductive, but in practice they are insulating. And vanadium dioxide is an example of such materials. And what happens is that they cannot conduct because of Coulomb repulsion from the electrons. But if we go up in temperature, we have a crystal switching, lattice switching in the device, in the material, from monoclinic to rutile. And then we have the switching. Now in this new lattice structure, the electrons can flow, and we have metal insulator to metal transition. Here we see the resistivity versus temperature. This is like a kind of textbook graph that you can achieve in laboratory. And we have a gigantic switching here. However, when we remove the excitation, when we remove the temperature, for example, in this case, the device reverts back to the insulating phase. And this is not what we want for a memory device that can carry information for a long time. So our observation was that it's true that the device comes back to the insulating state, but if we take a look at the next triggering of the device, we see the considerable memory, which is not what we expected. So here is the experimental setup that we have. So here we have the vanadium dioxide that is triggered by a function generator. And then we collect current in the second terminal, and we measure that with an oscilloscope. So let's take a look at the very first curve here. So we apply the pulse at 0, let's say. Then we have a time that the device is insulating. It's called incubation time of the device. And after some time, the device jumps up, switches, and goes to the conductive mode. The conductance goes up. So this is like a typical thing that we expect. However, if we take a look at this switching delay, this incubation time, we see that it carries an enormous information of the previous triggerings in the devices. So the way we performed the measurement was that we applied the very first pulse, and we measured an incubation time of 1.4 microseconds. So this is the very first switching. We had to wait, so the device, it takes 1.4 microsecond until it reaches to the point that switches to the conductive mode. However, in the second pulse, when we applied the pulse, the second pulse after 10 milliseconds, we measured an incubation time, which was very, very different from the first switch. And if we change this relaxation time from 10 milliseconds, if instead of 10 milliseconds, we now wait 100 milliseconds, we measure another incubation time. If we wait 1 second, we measure another incubation time. And here we perform measurements up to 10,000 seconds. So it depends on how fast this triggering takes place, we can understand the history and the memory of the previous switching. And this thing is not something that we classically expect from vanadium dioxide. So here we have the incubation time. This is the delay that we measure based on the versus relaxation time, how much it relaxed and what's the incubation time. And we see a logarithmic dependence here based on these two. And it's very interesting to note that incubation time carries the information of the previous switchings, but for example, not the conductance. If we take a look at the conductance of the same device, basically the values that we measure are within the error bar. There is no information in the static state of the device. But if we see the incubation time of a firing, we can understand when was the previous switching. And this is a unique thing about this thing. And then in another experiment, now instead of one pulse, we applied three pulses. We applied multiple pulses. And interestingly, we understood that by changing the number of pulses that we apply in a pulse packet, and after waiting for a long time, we can manipulate the incubation time in the sense pulse. And here we have the incubation time corresponding to different number of pulses from 1 to 100 pulses. So this means that we have an electronic switch that we can manipulate with the number of pulses that we apply. And to understand the origin of this effect, we first examine whether this can be thermal. We integrated the device with thermal heaters, integrated heaters, and we obtained the memory. So this means that the current that flows to the device and the electron migration doesn't produce this memory. We also examined whether metal to VO2 junction originates this by making a cross device. We examine this thing. We triggered the device in the horizontal direction and then measured it in the vertical direction. So we just manipulated the VO2 right at the middle of the cross. We don't anything at the metal VO2 junction, and we changed the incubation time in the vertical direction. And this proved that VO2 metal doesn't play a role in this new effect. And also the dimension of the device, we obtained that this is a scaleless device and can be obtained identically within devices with gap lengths of 50 nanometer to 500 nanometer. So this is a scaleless effect. And we obtained that this is probably not an electronic effect. And why not? Because we measured the same effect under green laser. Green laser has a photon energy above the band gap of vanadium dioxide. So we were thinking that if anything like a trapped state or any other electronic state within the band gap can carry this information, if we shine this device with a green laser, we should erase the memory because we reshuffle all the slates. However, we obtained identical results, which suggested that this is an electron, this is a structural effect. And very interestingly, we obtained, uh, in fact, a faster relaxation close to the transition temperature of the devices. And it's very interesting because we had a logarithmic relaxation, we had a structural state, and we have a faster relaxation close to the transition temperature. And these are all features of glass-like states that were known in mechanics. And that's why we called it glass-like effect in vanadium dioxide. And we fabricated also ultra scale devices. So here we have a device that we can achieve these performances in sub nanosecond time scales and picojoule, zero point 0.1 picojoule energy consumption, which is very interesting for memory devices, especially for multi-level memory devices. And also we showed that, in fact, this is very relevant to computational devices. And the fact is that incubation time is basically proportional to the energy barrier of the switching. So basically by manipulating the incubation time, we are manipulating the energy barrier of insulator to metal transition. And we showed that this is very, very interesting for neuromorphic computation. So here we performed a simulation, and we had a network here to have this effect, and we could demonstrate a classifier based on this new electronic functionality. And this work was published very recently in Nature Electronics, and we were very glad to have the also cover page on this work. So at the end, I conclude the talk. So we talked about three different device technologies: nanoplasma devices, which are very interesting for high power generation at terahertz frequencies. They can overcome the PFS square limit of traditional electronics. We had electronic meta devices, which is an interesting concept for terahertz electronics based on semiconductor platforms. And We demonstrated terahertz switches, high performance terahertz switches, which are relevant to ultra high speed 6G communications. And also we showed a new electronic functionality in vanadium dioxide, which is relevant to high performance memories, ultra fast memories, and as well as analog computations. And with that, I thank you very much, and we'd be happy to have if there's any questions.
Okay, thank you so much. Thank you so much
Thank you.
for showing the very new electronics, and, which is quite new, so maybe it is not so easy to understand clearly. So there may be a lot of questions, maybe, maybe. So, do you have any questions? If you have questions, please raise your hand, or the panelists can directly ask questions. Okay, maybe, yeah, it's not so easy to
Yeah,
really understand. So,
yeah. So the perspective is very nice, but as you mentioned, because the
mhm,
concepts are like very new,
mhm.
that could be a bit different.
Yeah, yeah, yeah. I'd like to ask first for the second subject.
Hmm.
Yeah, is it yeah, can we use it as a digital signal technology, or it's
Hmm.
like a on-off switching?
Yeah. So for in fact, I can show you this. So the difference here is that this is the schematic of the device.
Mm-hmm,
So this is intrinsically an RF device, which means
mm-hmm,
that we cannot have a DC signal
mm-hmm,
in this device technology.
mm-hmm,
However, I'm sure you're familiar with like analog optical computations,
mm-hmm,
that they have an optical medium,
mm-hmm,
and then based on different effects like Brewster effects and so on, they
mm-hmm,
can do the computation. And the thing that we are thinking now is that, let's say we have a nonlinear network based on these devices,
mm-hmm,
and then we apply signals like analog pulses from certain nodes,
mm-hmm.
and then we collect signals from certain outputs.
Oh,
And this can gives us a way to compute. And of course, we use these devices because they are extremely fast and they can respond to very short
mm-hmm,
pulses.
mm-hmm, mm-hmm.
Yeah, we are considering this actually.
Oh, I see. And for first subject, you know, yeah, I cannot understand how to control the frequency.
Mhm.
Yeah, could you explain the concept of controlling the frequency? Or?
Yeah, exactly. So here what we have, so the switch is a picosecond switch, right? And
Mm-hmm,
then in this case,
mm-hmm,
we have the bow tie antenna. And this bow tie antenna determines the frequency, because, so if we take a look, for example, at S21, the
mm-hmm.
transmission from the first one to the second one, it gives us a peak, right?
Oh, I see.
And then we are switching a resonator with
Mm-hmm,
picosecond time, and then we
mm-hmm,
have what the resonator gives us. But the
mm-hmm,
cool thing is that, okay, with like metallic structures, it's possible to make like antennas at 1 terahertz, but there is no
mm-hmm,
switch that can
mm-hmm,
activate that resonator. And
mm-hmm.
here, this nanoplasma switch, because it's a super fast switch, can now activate resonance frequencies in the terahertz range.
Oh, I
Yeah,
see. So is it like a filter, or?
actually, it can be a filter. So we have
Uh,
another very recent paper that was
mm,
published a few months ago,
mm-hmm,
and we designed a coplanar filter
mm-hmm,
between the input and output.
mm-hmm,
In fact, in the input, we have the ultra wideband signal from the nanoplasma, and the
mm-hmm,
output, we have the shape that we want based
mm-hmm.
on the linear network that we have. that we have in between. Here it is both filter and the radiating element. So we
Oh, I
have the
see.
radiation at the end.
Ah, I see. I see. Okay, thank you.
Thank you.
So, other questions or yeah, we have the high frequency device specialist, Professor Hala. Do you?
Hello? Okay.
Hello.
Yeah, hello. It's very too new for me to understand. I am a circuit designer, and we will try to realize over 100 gigahertz circuit by using electric devices. So, as you said, that your switch to the meta to the device is only for RF. So we cannot measure the so-called IV curve for this device.
Exactly. For the meta devices, there is no IV curve. Yeah.
So I'm curious, how do you define the R1
exactly
for that device?
So this is the standard S parameter measurement that we have. This is a two-port setup. So we have the device on the test here, and with a VNA, we measure the S parameter, right? And the S parameter gives the full information of the impedance of the device on the test. So it gives us the resistance and the capacitance.
Okay, I understand. So you extract the R1 and C at each frequency point.
Exactly. And here we have the plots for the on state and for the off state. This is very similar to characterization of transistors at high frequencies, like the GM at high frequency, the way they characterize.
And one surprising thing for me is you have the measurement system for roughly 1 terahertz.
Yep. This particular measurement was done at Fraunhofer Institute in Freiburg. In our lab at EPFL, we have potential to go up to 750 gigahertz.
Oh, we have only 100 gigahertz.
But these are extenders. So with the same, for example, if you have a 50 gigahertz VNA or 40 gigahertz VNA, with the extender module, it's possible to go up all the way to the terahertz band.
Okay. So how about the so-called turn-on voltage of this device?
The turn-on voltage of so I think I have some extra slides here to show and this could be also interesting because here we have the circuit modeling of these devices as well. So the threshold voltage, so these are normally on devices based on gallium nitride. So at 0 volt, it's in the on state. And then the threshold voltage is about 4.5 volts. So, and for the modulation experiment from the circuit side, we had a bias T. We basically biased the devices at 4 volts, let's say. And then with a 1 volt peak to peak signal, we basically modulate the device with the data signal that we had.
So this device can be used for the mixing, but cannot be used for rectifier, right?
So a very interesting thing is that now that we demonstrated the 3-terminal, just show you again. Yeah. So now that we demonstrated the 3-terminal devices that I showed in the slides, it gives us opportunity to do almost everything that we want. The most important thing that we are looking at is now an amplifier. But what we have done rectification also based on that devices, because when we bias the device, when we apply a positive voltage to the gate signal, only one signal direction can pass through, for instance. So we had the rectification capability too.
Could you move to the slide which showed the 3-terminal?
Yeah, sure. So I just this again. Great. So this is the 3-terminal device that we know. Yeah. This is the yeah. This is the 3-terminal
this one.
device. Yeah.
3-gate control. Ah, so the gate control means how to say, you put kind of some threshold control between the RO in and RO out.
Between sorry, between what and what?
You show the two-terminal meta-to-deck switch. Previous slide you show the how say the performance is symmetrical. So you shift the center point by the gate control. Right?
Yeah, exactly.
Okay.
Exactly. It's possible to do that. Yeah.
Okay, I understand. Thank you very much. And I have to show my face at last.
Thank you. Thank you for the question.
Harasaki.
There's also one question, I guess.
Yes.
Yeah.
So there is one question. Chen-san, maybe you can talk or no? Your mic is muted. Okay. Chen-san, can you? Oh, okay, good. Still.
Oh, hi, Mohammad.
Hello. Yeah.
I want to ask the question is, when you talk about output power, I want to know you are talking the peak power or the average power. Like you can output 2 watt at 300 gigahertz. You can the 2 watt means the peak power or the average power.
So in that case, 2 watts was the average power. Noting that we can have a very high repetition rate also with these devices, but the value of 2 watts is the peak power.
So the average rate can reach what?
So it depends how fast we switch. We have shown switching above 100 megahertz, but it's also the case that because these devices are very simple and small, we can also integrate them, a lot of them, with a phase delay. So we can achieve basically an almost continuous wave output by scaling up. Yeah.
Oh, so 100 megahertz for the device lifetime can be a challenge, right? 100 megahertz if it really works at such high frequency.
Yeah, for the lifetime, that's also a very good question. So currently with tungsten material, with 1 micrometer tungsten, we have very good lifetimes, and we are working now on single crystal metal to have basically infinite lifetime for these devices. So it's very interesting that if you look at papers for CMOS papers like 20 years ago or something, the electromigration was a serious challenge for them because they had interconnects, and because of the current in the interconnects, after some time, they were just, they broke. And then at that time, we found several papers that use single crystal aluminum. They could totally resolve this electromigration thing. And we believe that using single crystal metal for nanoplasma devices is a way to have an infinite, basically.
Many thanks for your
thank you very much for the question.
And thank you for the host.
Thank you.
Thanks.
And we have another questions. Mr. Mohammad Go bamboo. Mr. MG-san. Go bamboo-san. Can you hear me? So you can talk. Mohsen is your friend, Mohammed?
He's my colleague at ETH.
Oh, really?
Yeah.
So
I think he can speak now. He's not mute, but we cannot hear you, Mohsen. So he wrote
sorry,
something. My mic is not working. Okay, maybe you can write his question.
Yeah, could you write the question? So we will wait for.
So because your department has, I mean, extensive experience in growth, have you tried metal growth?
Metal?
Yeah.
Metal growth means a single crystal, you mean?
Yeah, single crystal.
Oh, no.
Okay.
From my perspective as IC designer. Okay, before writing the question, I'd like to ask the Professor Yuji Ando for the comments on the questions.
Yes.
Sir.
Can you hear me?
Yes, yes.
Yeah, I'm Yuji Ando. I'm working on the gallium nitride microwave helmets. Thank you very much for your very interesting talk. And I have a question about your first device. May I see your slide number 7?
Yeah, sure. Yep.
Yes, I have a question about the threshold voltage of your device. And yes.
Yeah.
Threshold voltage of your device is about 40 volts for the gap separation of 300 nanometers. I think this VTH value is very close to the breakdown voltage of gallium nitride HEMS with the same gap separation. Yeah, in the case of gallium nitride HEMS, breakdown voltage is about 30 volts for the gate drain separation of 300 nanometers. And so VTH of your device is very close to the breakdown voltage of gallium nitride HEMS with just similar gap lengths. And I think the barrier height of your device is close to the work function of metal. Maybe it is gold.
Yeah, in this case, it's gold.
Gold. So it should be around 5 eV. Is that right?
Yeah, it's about that.
And the gallium nitride HEMS, the Schottky barrier height is just 1 eV. So why does your device show such a small VTH value?
Yeah. So here, apart from the work function, so if you take a look at the mechanism of these devices now, so for larger scale spark gaps, the way they worked was based on Townsend avalanche. So they had Townsend avalanche for larger scale devices, and then they had some electrons that, I mean, the conventional like avalanche process initiated those plasmas. For these devices, because we are within the mean free path of electrons in air, in this case, people believe that there is a combination of the two. So combination of the field emission as well as the avalanche process that initiates this thing. And so and interestingly, it doesn't depend much at the end, the threshold voltage, on the type of the metal that's used. At least between gold and tungsten, this is what we know. So the process, and it's very interesting that the very process of this plasma triggering is still under debate, because 20 years ago or 30 years ago, people thought that at these scales, they cannot fire plasma. They cannot initiate plasma, because if you take a look at the Paschen law, Paschen curve, which is breakdown voltage versus pressure times distance of a gap, it drops until some point, there is a plateau, and then it goes up. And it's clear, because it's very small scale, you cannot have avalanche that easily. So they thought that there won't be a plasma in these scales. But then when they prove that this is a plasma, and we also prove that this is a real plasma based on optical emission spectroscopy, then for a decade or so, some research group are looking for the mechanism of this thing, and is still under debate. So that's why this is like an open question, that what is the very first mechanism that initiate this plasma to identify the threshold voltage of that.
Oh, so you mean mechanism is different from the
Mechanism?
Yeah.
Yeah, sure. With Schottky barrier is different, and also the mechanism is different from large scale plasmas, because we are within the mean free path of electrons.
Okay, thank you.
Thank you.
Thank you, Ando Sensei. Are there any questions? Mosen-san.
Hello, can you hear me?
Hello. Yeah.
Yeah. Okay.
Sorry, I was using my Linux machine, so it basically didn't detect the microphone. No, I changed to my phone. I'm actually a circuit designer, and from my perspective, in your first talk, you were talking about the PF square limitation, but from my perspective, I think that you are talking about the output capacitance, but we can take into account the output capacitance in a tank resonator. So the only limitation is gonna be, at the output of our power amplifier, for example. The problem would be possibly the cutoff frequency, because in that frequency we won't have any power gain received, or another limitation could be for us the saturation of the power amplifier, which is limited by the process actually, and we cannot, we can somewhat improve the output power by changing the output impedance ratio, but the problem is that even increasing this ratio might have some problems for us. For example, we have more loss in the transformation and stuff like that. But I cannot quite understand the PF square limitation, because I guess we can just take into account the output capacitance as a resonator with a inductor.
Yeah. So this is for a class like a conventional single transistor amplifier that we talked about in this particular circuit, and also the Johnson's figure of merit, which is known in the field, that takes into account the saturation velocity of electrons and the critical electric field, and this shows how fast a transistor can process an electrical signals. It gives the dV/dt of that. And if you see the benchmark of different technologies for the Johnson's figure of merit, like GaN is above all of them. And you can see that the transistors with the highest mobility, the very best 3.5 transistors like gallium arsenide, they are like below 1 volt per picosecond, right? And in this graph that we had, this is like the output power of what people have achieved. So you can also see this theoretical prediction of PF square also in commercial sources.
Yeah, for sure. I can understand, the graph and the limitation, but the concept that, it's the output capacitance that is limiting us. I cannot quite understand that concept. You know,
Yeah, this is for this circuit topology that we were talking about.
Okay, but you
Yeah.
know, you have a Z load impedance, even in this topology. So in that Z load impedance, you can just have an inductor which is going to resonate in that frequency you are going to work.
Yeah,
you know?
but we have to also take into account that the highest amplifiers, the amplifiers at the highest frequency are basically the simplest one, because they cannot make like a good inductor operating at 1 terahertz to compensate what they have. So it's a single transistor that is limited by that is terminated by the load basically. And so, yeah.
I see, but at least, you know, I'm not that much expert into compound technologies, but at least in CMOS technologies, just simply can have high quality factor transmission lines.
At 10 gigahertz, it works, yeah.
And I'm not talking about 10 gigahertz, you know, I'm talking about 200, 300 gigahertz. We can achieve quality factors above, let's say, 10, maybe. So it's still achievable. You know, the limitation, at least as a circuit designer, for me in CMOS technologies, the limitation is gonna be the cutoff frequency, because above that frequency, we're not gonna have power gain. It's obvious, but you know, if we have a power gain available, we can just have multiple stages to achieve the output power we desire, but it's still limited by the, you know, process parameters like the saturation current and saturation voltage and stuff like that, the maximum voltage that the transistor can tolerate and stuff like that.
Yeah, exactly. And also please note that when you talk about compensation of output capacitance, so here we are talking about the transistor, how much it can, in this specific thing, how much it can generate power versus frequency. At a certain frequency, you can compensate what you have in the output, which is the case for like narrowband amplifiers, but again it will drop. And as you mentioned, above like 300 gigahertz or so, or if you look at 1 terahertz, it's extremely difficult to have a decent quality factor to compensate the output capacitance and so on. And this is, as I mentioned, is one part of the thing. Another theoretical part is the Johnson's figure of merit, which again dictates the PFS square.
I see.
Yeah.
Thank you.
Thank you.
Sorry for inconvenience. I couldn't connect.
Thank you very much.
Thank you. Okay, any other questions? Okay, no. Okay, then thank you, Mohammad, for the excellent presentation and showing us new electronics.
Thank you very much for this opportunity.
Yeah,
thank you
so
very
much.
I appreciate it.
Yeah, thank you.
Thank you.
So now it's the end of this seminar. Thank you so much.
Thank you.
And bye-bye.
Bye-bye.
Thank you.
Thank
Bye.
you.
Bye-bye. Oh, maybe it is better to take a photo. Just
sure.
a moment. Yeah, just a moment. Okay. Oh, yes, thank you. Hara-sensei is gone. Okay. Thank you so much.
Thank you.
Yeah, thank you.
Thank you. Bye-bye.
Have a good evening in Japan and all over the world. Have a good time.
Oh,
Bye-bye.
the Hara-sensei is coming. Just a moment.
Yeah, sure.
Hara-sensei, can you put the video on?
はいはい。すみません。なんか 天野先生がなんか喋りかけて、退出ボタンを押したし、いいなんで入る
Oh, okay, okay. Okay,
ちょっと、
okay. I can
光の関係で見えない。
I can take a picture. Okay, thank you. So now you are it's 7 hours difference. So
It's
will
noon here.
oh no.
Yeah.
Yeah. So how about it?
20 past.
Good.
Great.
Yeah. Good afternoon.
Perfect. Thank you very much again.
you.
And
Thank you.
bye bye.
Bye bye.
はい。